Please don't forget to like, subscribe, and comment. Thank you so much.
Join us at Like Learning School and experience a transformative education journey. Visit our website at www.likelearningschool.com or contact us at +234 808 509 5144 to learn more and get started today.
For the second law, for Newton's second law, we already established that the second law is about momentum. And the full statement of the second law is the rate of change of momentum is directly proportional to the applied force. So second law definition or statement of the second law in terms of momentum. Newton's second law of motion in terms of momentum. In terms of momentum, it says the rate of change of momentum is directly proportional to the resultant force. And it takes place in the direction of the resultant force. So the rate of change of momentum is directly proportional to the resultant force, and it takes place in the direction of the resultant force. Momentum itself is mass times velocity. A simple illustration could be this. If an object of mass m starts with an initial velocity u, and later this same object of the same mass changes to another velocity v, same mass m. The momentum or initial momentum is mu. The final momentum is mv. Change in momentum will be is equal to, change in momentum is mv minus mu, because change is about the difference. Remember, the initial momentum is mu, the final momentum is mv. Let me call this initial momentum. While this one is final momentum. I think we can write it better so that it will come out clearer. This first one is initial momentum. Let's clean this and put it in the other way. So So this first one is initial momentum. While this second one is final momentum. So initial momentum mu, final momentum mv, change in momentum, the difference, which is mv minus mu. That's for change in momentum. Now rate of change of momentum. Rate of change of momentum is equal to, when we talk about rate, we measure the quantity with respect to time. So mv minus mu divided by time, or m, if we factorize, we have v minus u all over time. Factorizing out m, if m comes out, we have v minus u over t, and we know that v minus u over t is acceleration. V minus u over t is acceleration. So this whole thing becomes ma, and from the initial way we studied it, ma is equal to force. Since ma is equal to force, it means force is the rate of change of momentum. So this is equal to force based from our initial explanation. Ma is force. So that force is the rate of change of momentum. Is the rate of change of momentum. Mv minus mu over t. So force is proportional to the rate of change of momentum. That's what we have written here. Or the rate of change of momentum is directly proportional to the resultant force. Remember, this F stands for resultant force. Okay, we have seen that force is equal to, or resultant force is equal to mv minus mu over t. Which is the Newton's second law. Resultant force F is equal to mv minus mu over t. By the way, mv minus mu is change of momentum. So resultant force is the same thing as change of momentum over time. Divided by time. So resultant force is change of momentum over time, or F equal to mv minus mu over t. If we cross multiply, we're going to have Ft is equal to mv minus mu. So Ft, or force times time, is a quantity we call impulse. So this is impulse. This gives us impulse. And mv minus mu is change of momentum. Therefore, impulse is the same thing as change of momentum. Impulse is the same as change of momentum. The unit of impulse, since impulse is force times time, impulse itself is force times time, the unit of impulse should be, let's write the units here for each of them. For impulse, the unit is Newton seconds because it's about force and time. Force times time or Newton seconds. While the unit of momentum is mass times velocity. Mass times velocity, mass times velocity. So unit of momentum is kilogram meter per second. Now that means Newton second is homogeneously the same as kilogram meter per second. We can prove that when we reduce them to their base units, their SI units. Newton second and kilogram meter per second are homogeneously the same, because impulse is the same as change of momentum. Remember, impulse Ft is mv minus mu. We got that from this. So we can see that from F equal to mv minus mu over t, F equal to mv minus mu over t, when t becomes smaller, the force becomes bigger. So for a change of momentum, from F equal to mv minus mu over t, all divided by time, as t decreases, or during an impact, or when t decreases in an impact, the resultant force becomes bigger, because when t is smaller, it means F is going to be bigger. When you have a smaller value of t, if mv minus mu divided by the smaller value of t will produce a bigger force. So from F equal to mv minus mu over t, that's this, mv minus mu over t, when t decreases in an impact, there's a bigger effect on the force. There's an increased force of impact. So when t decreases in an impact, the implication will be an increased force. When t is smaller, the impact force reduces. One of the ways this can find useful application is in collisions. For instance, when there's an accident, with the use of a seat belt or an airbag, the time of impact is increased, because with the airbag in place, or the seat belt in place, the time of impact is increased instead of a sudden collision with maybe the steering. But if you have a seat belt, you're wearing a seat belt, or there's an airbag, the time of collision is increased. This T becomes bigger, which reduces the impact force on the person who is driving. So that will help to reduce injury. So that's why there's a need to put on your seat belt and have the airbag on the steering working, because with the seat belt in place or the airbag working properly, if there's a sudden collision, the seat belt will prevent the collision to happen in a very short time, because with the seat belt or the airbag, it prolongs the length of the collision. It drags it longer because you are wearing a seat belt, or because of the airbag, it drags the collision longer than it would have been if there was no seat belt or the airbag was not working. So with the seat belt or the airbag, it increases the time of the collision, which of course means there will be a smaller force of impact that the driver will feel. So when T decreases in an impact, there's an increased force. So in the other way around, when T increases, especially with the use of an airbag or a seat belt, and the time of impact increases, the effect will be a decreased force of impact, which reduces injury. It's a safety precaution.
Do you know the principle of conservation of linear momentum? No, that's energy. That's energy. I'm talking about momentum. The principle of conservation of momentum. Momentum is total momentum before collision is equal to total momentum after collision. Let me write it down. Before collision is equal to total momentum after collision, or even before separation. But let me not go into the details. Collision or separation is equal to total momentum before collision. Total momentum after collision or separation. Read what I wrote. Now it says, explain how this momentum is conserved. Use Newton's third law and second law in your answer. You know, the third law states that for every action, there's an equal and opposite reaction, right? There is an equal and opposite reaction. I want to state all this. Then, second law states that the rate of change of momentum is directly proportional to the force. This is third law. Second law states that the rate of change of momentum the third law was what? Action is equal to reaction, and they are equal and opposite. It's proportional. Resultant force. So, this principle of conservation of momentum, look at this. If you have an object, I have an object like this. Are you ready for this? Moving with a velocity of 3 meters per second. It has a mass of 5 kg. Then another object, which I will draw with a yellow, has a mass of 8 kg or even 7 kg, whatever you like. It moves with a velocity of 2 meters per second, or let's say this one is moving with 8 or 7 or 6. Let me just make it slightly different. This one is moving with 2 meters per second, but this is moving in the opposite direction, right? I call this one object A and call this one object B. The principle of conservation of momentum, linear momentum, says that total momentum before collision, let me rule a line here, before collision equals total momentum after collision. What's momentum, by the way? Mass times velocity. Momentum is mass times velocity, okay? Momentum is what? By the way, before they collided, what's the momentum, their total momentum before they collided? You know, you calculate the momentum of A and then the momentum of B, you add them together. That's their total momentum before, because the principle says total momentum before collision. So let's find the total momentum before they collided, which is the momentum of A plus the momentum of B, right? So what's the momentum of A? So 6 times 5, or 5 times 6 if you like. 5 times 6, that's for A, plus momentum of B. Now, because it is moving in the opposite direction, momentum is a vector quantity. If it is moving in the opposite direction, you have to use negative for the velocity, okay? So 7 times minus 2. The reason is because it's moving in the opposite direction, okay? So this is total before. Total before. So 5 times 6 gives us 30 plus minus 14. That's 26 kilogram. Is that 26 or 16? 16 kilogram meter per second. If momentum is mass times velocity, what should be the unit? Unit of kilogram is kg. Unit of speed is meter per second. So the unit should be kilogram meter per second, okay? So this is the total momentum before collision. Now, so that I don't waste time, assuming these two objects now collided and they are sticking together like this. They collided and they coalesce, what we call coalescing, sticking together. This is 5 kg. This one is still 7 kg, but they are now sticking together. What will now be their common speed, and which direction will it move? This is before. This is now after. So let's find, what did we get as the total momentum before collision? Let's find the total momentum after. Are you ready? Assuming they are now moving with a speed of v, we don't know. They're moving with a speed of v, we don't know what it is. Let me even show its direction the other way. We can show the direction anyway, but we don't know what it is. But both of them are now moving with a speed of v. We need to know what v is. We can calculate that v. What's their momentum after collision? What did you say momentum is again? So what will be the total momentum after collision? Where do you get 35? 5 times what? 7 is mass, 5 is mass. The speed is v, we don't know. Interesting. So 5 plus 7 times v, which is actually 12v, isn't it? 5 plus 7, is it not 12? Yes. Yes, now, you see, what's momentum? What's the total mass? 5 plus 7 times the velocity. So 12v, 12v. Mass times velocity. We don't know what this v is. That's actually what we're calculating. So this is the momentum after. This is the momentum what? What's the value? 12 what? What's the momentum before? So let's apply that rule. Oh, sorry, this is before equal to after. Before equals after. So you equate. What is before? 6 equals 12v, right? 16 equals 12v. So you can easily calculate v. So v will be equal to what? 16 over 12. And what does that give? 4 over 3. Isn't it? 4 over 3 meter per second. By the way, we didn't know the direction the speed will. You see, it's like one object is moving this way. It collides with another object moving the other way. And they join together. Which direction will they move after they have joined together? And what speed will they move in that direction? The direction they will move, we don't know. I can just assume it to be going to the right. I could have assumed that it's going to the left. This is how we know the direction. This answer we got, is it positive or negative? That means the direction we assumed it is right. That is the correct way. But if it was negative, that means it was actually going the other way. So you can actually say, because velocity is a vector quantity, so you can say the velocity is that common velocity with which they will move now. Therefore, common velocity after collision. Let me just summarize with that. Therefore, their common velocity after collision is equal to 4 over 3, which is 1.333, isn't it? 1.33 meter per second. To what direction? In what direction? To the right. Because the direction will assume it turns out positive. So you don't have any problem. You just assume it in any direction. If it turns out positive, it means it's the right direction it will move. But if it turns out negative, it's the other way it should move. Okay.
All right, can we do this very quickly? Are you ready? Let's read out this B part. It says a metal block traveling in a straight line at 4 meters per second on a smooth surface collide with a second metal block B, which is at rest as shown. And it says the two metal blocks A and B before and after collision, are shown in this diagram. Before collision, what's the speed of A, block A? Is everybody listening? Is everybody listening? Can I good. Can I hear Imonia? Are you listening, Imonia? That's the speed of A. What's the mass of A before what's the mass of A? What's the mass of B? What's the speed of B? The speed of B is 0, because it is at rest, so the speed is 0, which is 0 meters per second. All right, after collision, what's the speed of A? We are looking for the speed of B, right? Good. All right. I want us to do something very quickly here. There's a principle you will have to apply here. That's the principle of conservation of linear momentum. Let me write it down. The principle of make sure you are looking at the screen. I'm sharing my screen. Can you all see my screen that I'm sharing? The principle of conservation of linear momentum. Linear momentum. What does that principle state? Can anybody state that? Yeah, go ahead and say it. Beautiful. The principle of conservation of linear momentum states that total momentum before collision is equal to total momentum after collision. Did you all hear that? All right, let me write it down. Total momentum before collision equal to total momentum after collision. Total momentum before collision is equal to total momentum after collision. After. That also means total momentum before separation is equal to total momentum after separation. It can be collision or separation. Is momentum I wanted to write. Is total momentum. Let me write it properly. Total momentum before collision equal to total momentum after collision, right? That's the principle you should always apply. Please listen very attentively. Total momentum before collision is always equal to total momentum after collision, right? You can apply it here and look for what is not given. For instance, the speed of this object after collision is not given. You can find it. Can we do it now? Okay, so total momentum before collision. Total before collision, or let me just write before collision. Let's get the total. Before collision, what's the total? mass times velocity of this one, which is 3.2 times 4.0 plus, what's the momentum of this of B? Times 0, and that gives us what? .8 kilograms meter per second. Let's find the total momentum after collision, because they must be equal, and then we equate both. So that is total before collision is 3.2 times 4.0 plus 1.6 times 0. That gives us 12.8 kilogram meter per second. So after collision, what's the total momentum? Total after. First of all, let's add them up the way we added up the one before collision. So you add the momentum of this one and the momentum of this one. What's the momentum of A? If the speed is now 1.5 meter per second, let's go. Let's go. What's the momentum of A? You will write 3.2, that's the mass, times 1.5. Okay, that is for A, plus the momentum of B. What's the momentum of B? Times what? The momentum of B is 1.6 V. Momentum of A, hold on, momentum of A is 3.2 times 1.5. I've written that. That's momentum of A, because the speed is 1.5, the mass is 3.2. Momentum of B is 1.6, because the mass is 1.6, times velocity V times V. Okay, so we've written that. First of all, what was the total momentum before collision? What was the total momentum before collision? And what is the total momentum after collision? Good. So we have total momentum before collision 12.8 kilogram meter per second. Total momentum after collision is 3.2 plus 1.5. 3.2 times 1.5 times 3.2 times 1.5 plus 1.6 V. All right, so we have this. Let's equate both. Total before equal to total after. So let me write it down. Total before equals total after. You can use that to find what you're looking for. Can you see what I'm writing? Total before is 12.8. So we have 12.8 for total before equals total after is 3.2 times 1.5. What is 3.2 times 1.5, by the way? It's 4.8, right? 3.2 times 1.5 is, did you say it's 4.8? Total before is equal to total after. That is the principle of conservation of linear momentum. Total momentum before collision is equal to total momentum after collision. So 12.8 is equal to 4.8 plus 1.6 V. Solve the equation to find V. You can solve the equation now. V is what? You found V to be 5, right? 5 meters per second. Now, because it is positive, it means it is going in the same direction as A. You know, I always told you, you see, A is going in the right direction, right? Are you listening to me? Since A is going in the right direction and you made it positive, the V you found, which is also positive, is also going in the right direction. If we found it and we got negative, it means it's actually going in the opposite direction, okay? Because momentum is a vector quantity. Now, look at this question. Let me not prompt you, so I will clean what is already written here. Let's solve for C. It says, in the collision that occurred in B, block A and block B are in contact for 0.50 seconds. Calculate the average force that is exerted on B during the collision. How do we calculate the force? I hope you know that impulse is change in momentum. Impulse is equal to change in momentum. Impulse, which is I, is equal to Ft, which is change in momentum, mv minus mu. Is it not? Impulse, which is Ft, is mv minus mu. Change in momentum. All right. So what's the change in momentum in B? That's what you should be looking for now. What's the change in momentum that occurred in B? How will you find the change in momentum in B? Beautiful. What's the mass of B? Mass times... Okay. Mass of B is 1.6. So we have 1.6 times... What's the final velocity of B now? 5 minus the mass of B, 1.6. Then times... What was the initial velocity? 0. And it's equal to impulse. Because the question is about calculate the average force that is exerted on B. On what? So you should be Yes. So you can get the force. Interesting. So we don't have the force, but we are given the time. The time is 0.050. So we simply do that force we don't know times 0.050. So F times 0.050 is equal to all that. So okay, the whole of this side is 8, right? The whole of 1.6 times 5 minus 1.6 times 0 will give us 8, yes. Beautiful. So F will now be equal to this whole place, which is 8 divided by 0.050. So the force is, what's the value of the force now? The value of the force will be 8 divided by 0.050, which is what? Okay, it says after the collision in B, the total kinetic energy of the two blocks is less than the kinetic energy of blocks A before the collision. Suggest one reason for this. So, Imonia, suggest one reason for this. Energy is lost. But energy is lost. In one way, is the energy lost? Friction, heat, sound. Energy is lost as heat, as sound. Because when there's a collision, there's usually sound produced. I just want us to check this out. Can you find the total kinetic energy before collision? What's the formula for kinetic energy? Formula for kinetic energy is half mv squared. So find the kinetic energy before collision, total kinetic energy before collision. $25.6 joules. 25.6 joules, right? What's the kinetic energy of B? 0, because the speed is 0, so everything will be 0. So kinetic energy of B will be 0. So this plus 0 will give us only that, 25.6 joules. That's the total kinetic energy before collision. Let's find the total kinetic energy after collision. After collision, total kinetic energy. Everybody, are you ready now? Kinetic energy is half mv squared, which is equal to half times the mass of A, 3.2 times the velocity of A squared, which is 1.5 squared. And that gives us 3.6, right? Okay, let's add it to the kinetic energy of B. What's the kinetic energy of B? We are working on after now. Half times you know why we are using 5? Because the speed of B we have found is 5, isn't it? So that's 3.6 plus 20. Is that? So what does this give? Okay, let me even put this in a bracket. Equals 23.6. Imonia, compare the kinetic energy before collision, total kinetic energy before collision, and the total kinetic energy after collision. What was the total kinetic energy before collision? What was the total kinetic energy before collision? Joules. What's the total kinetic energy after collision? What did you notice? Why did it reduce? In all cases of collision, total kinetic energy, especially if it is a practical one, which is inelastic. Total kinetic energy before collision is always bigger than total kinetic energy after collision. The only time they will be equal, and that is not practicable, we call that an ideal situation, is during perfectly elastic collision. And in perfectly elastic collision, total kinetic energy before collision is equal to total kinetic energy after collision. Let me write it down. We will end with that. Victoria, did you hear that? It is only in, let me write it down below here, it is only during a perfectly elastic collision that no energy is lost. So total kinetic energy before collision is equal to total kinetic energy after collision. Total KE before is equal to total KE after. Read what I just wrote in blue now, everybody. Read what I wrote in blue if you can see it. In that case, no energy is lost. But can I tell you that total energy before collision is always equal to total energy after collision, whether for inelastic or for elastic. We continue with the next question on the right. Can you do that? This question on the right, you have to continue with it. Everything here. All right. So,
please don't forget to like, subscribe, and comment. Thank you so much.
Welcome to Like Learning School, your premier online education platform. At Like Learning School, we are dedicated to helping students and learners unlock their full potential, providing them with the foundation, support, and guidance they need for academic excellence. Our platform caters to two main target audiences. Firstly, we work with school children of all ages, offering academic follow-up and accountability partnerships. Our seasoned tutors provide personalized attention to ensure students stay on track and reach their goals. Secondly, we support students and learners who are preparing for internal, external, entrance, or professional examinations. We offer comprehensive and well-structured support to help them achieve outstanding performance in their exams. Our robust virtual courses are designed to keep students engaged and motivated. With interactive videos showcasing our teaching sessions, students actively participate in the learning process, making education enjoyable and effective. But that's not all. We believe in personalized education. Our students have access to personalized tutorial sessions, whether online, physical, or hybrid, tailored to their unique learning needs. Join us at Like Learning School and experience a transformative education journey. Visit our website at www.likelearningschool.com or contact us at +234 808 509 5144 to learn more and get started today.